Hi, and welcome to day 5. So today we basically have just a transition state problem using a lot of ranges. So we start with a number of seeds, 79, 14, 55, 13, and then we have a set of transitions. So we're going to transfer seed numbers to soil numbers to fertilizers, fertilizers to water, blah, blah, blah. And then we want to return the minimum number when we're done. And so the way these lines work is anything that's in the range of 98 with a size of 2, so 98 and 99, then we want to transfer that to a range of 50 with a size of 2, so 50 to 51. So we want to translate 98 to 50 and 99 to 51. We don't have anything that's 98 or 99, so this line basically does nothing for this one. The second line though catches a couple, so that's 50 to 48, or 50 with a size of 48. So that's 50 to 97. Again, fence post, we don't use the last one. So that will catch 79 and 15. And it's going to transfer that to a range of 52 to 99. So basically, we're going to add 2 to anything that's in the range of 50 to 97. So this is going to become 81. This stays at 14 because it didn't match anything. This becomes 57 because it matched the second one. And then the 13 stays 13 because it didn't match anything. And then we take those new 4 numbers and we plug them into the second set and the third set and the fourth, like each time we just go down the list. So to make it a little bit easier, I started with a range map, which basically is that same line. So we have our destination start and our source start and our size. And then I have a parsing function that basically takes that group. So this whole thing here, and we're going to ignore the first line and then do the second 2. So we're going to take the last n-1, ignoring the first line, split them on spaces, and then add them to our ranges and return back our range map. So all that does is just a fancy way of parsing those groups into lines. Then I have a convert range function, which basically will take a range map and a value. If that value is in that range, so again, using until because we don't want the end, we don't want the fence post problem. So we start with range source start all the way up until 1 less than range source start plus range dot size. So again, if the range is 50 and then the length is 10, 50 to until 60, so it gives us 50 to 99 or 59 as our range. And then if it's in that, we're going to do the math. So like the +2, the -2, whatever the transformation for that range is, we do that math and return it. Otherwise, we return null because it wasn't in the range. And then I have a map seed function, which is going to basically take all the groups for that transition, and it's going to take a singular seed number. And then for each group in the group transition, we're going to try to convert it. If it's not null, then it does convert, and so we return that. Otherwise, we go through all of the groups one by one, and this is going to go through each. Oh, it's also going to go through each group over and over. So basically, we'll do all the transitions together. So then part 1 is pretty simple then. So we take our first line of input, we split it on the colon space, so the seeds portion is going to be index 0, we throw it away, we don't care about it. And then index 1 is all of our numbers. We're going to split those on spaces and then map them to longs. Why longs? I didn't actually double check, but I saw a lot of big numbers, and if you see that, just use long, it's fine. And then our groups for each. So I have this helper function read space delimited because we see a lot of these in AdVent code where we have like these empty lines breaking up groups. And basically what this does is it converts this to a list of strings, it converts this to a list of strings, it converts this to a list of strings, and then it returns a list of strings. So this is like index 0 of the top list, this is index 1, which again is a sublist, this is index 2, so on. And so basically what I want to do is I want to take the last n-1, so I'm going to ignore the first one, that's the seed group, and then I'm going to parse that group and map that into groups. So that just gives me my list of groups. And then for each seed, I'm going to do this map seed, which again takes all the groups and a seed number and just parses through all the iterations one by one. until it gets to the end and throws out the seed number. And that gets mapped to seeds, and then I just need the minimum of that. So that's it, that's the answer. So for part 2, things of course get hairier, and there's basically 3 ways things get hairier. They either make it more complex, or they change the rules, or they make it too big for computation. In this case, it's the latter. So what we're going to do is, instead of this being seed 79, 14, 55, and 13, these are now new ranges again. So this is a range starting at 79 that is 14 long. So 93 minus 1, so 79 to 92. And then 55 to 67. And then we're going to have to consider all of the seeds in those ranges. For the sample input, that's whatever, it's a couple dozen, who cares. But for the real input, like this range is 100 million things long, right? I think one of them in here is like 800 million things long. That's a lot, so it's going to take a little bit of time. It's really not that much time, so I still just coded the naive way first. So I took my seeds, I split them on spaces, I do this operation chunked 2. What that does is it gives me lists of every 2 items. So it gives me a list of 79 and 14, it gives me a list of 55 and 13, and so on until it runs out of input. And then for each of those chunks of 2, then I'm going to map them to a new range that is basically the start number until the start number plus the length. And so now our seeds aren't individual numbers, they're now actually long ranges. Groups is exactly the same as it was before. And the naive approach, basically for each seed range in our seeds. So again, our seeds is now going to be, you know, the 79 to 93 or 90, yeah, and then so on, 55 to 62, whatever. And so for each of those ranges, for each seed in those ranges, we're going to compute the value for that seed exactly the way we did before. And if it's the new minimum, we take that. If it's not, we don't take that. And return our answer. Obviously, this is suboptimal. It took, I don't know, 5 to 10 minutes to run. I was going to time it, just never got around to it. Don't care. It was about 5 to 10 minutes. So obviously, it took a few minutes to run, but probably faster than trying to code it the correct way to start with. So that's what I did at the time. Afterwards, I came back to try to make it a little bit better, especially when I'm going to put it up on my GitHub, as I always do, link below. But what I did was I created this helper function here again that's going to basically consider everything not as discrete seeds, but as ranges. So for each transition that we have, we'll start with our current ranges. This is just the starting ranges that we have. And then for each transition, we're going to build up a list of new ranges for the next transition to start with. And the first thing we do is we find all intersections. So for all the ranges that we have, or for every range and current range, for every line in the transition, we're going to find that intersect. And if it's not empty, we're going to add it to our new ranges. And then the second one is we're going to go through and find all ones that don't have any intersects. So for each range in the ranges, we're going to have a new no intersects, and then for each line, we're going to go through and if it doesn't intersect, then we're going to map that, and we're going to check that line by line because it has to pass through all the lines in order to skip. And once we're done, we'll have a list of all of our ranges without any intersections. And then once both of those are done, we can change our current ranges to the new ranges, and then start the whole thing over again for the next set of transitions. So this should be quite a bit faster, because even though we might end up with hundreds of ranges, like, you know, you could think of like if you have a seed range of 0 to 100, and you have a mapped range of 50 to 60 or whatever. Well, now we have 3 new ranges. So we have a range that fell out that's 0 to 49, a range that's gotten mapped to some new value, and between 59 or 50 and 59, that's now some new value, and then 60 to 100 fell out, And then we have to do that for another line, another line, another line. So we could, our 0 to 100 could get spliced up multiple times. And then those splices will get spliced up multiple times the next transition and so forth. So we could end up with hundreds of ranges at the end of this, but that's not a big deal. And then after we have all those ranges, basically what we need to do is a lot simpler. We're just going to get our list of end ranges, and then we're going to map just the first values, because once we're done with all the transitions, we always want the smallest value of each range. That's going to be the first. And then we want the min of all of those, and then we're done. So this should be quite a bit faster, because instead of looking at hundreds of millions, billions of items, it's only looking at just the end ranges, just the end numbers, right? It's only caring about just doing the math at the top and the bottom. The problem is, to my surprise, the line I originally had was this one here. So I'm going to create a line source, or a range that starts at source until source plus start. Same way we've been doing ranges all the rest of the time. And I'm going to use the Kotlin intersect operator and intersect it with the range, the seed range. And this took a long time. It like literally was over a minute per iteration going through here, and it has to go through that, you know, a dozen times per transition, and then there's like a dozen transit, like it's a ridiculous amount of time. And I would have thought that it would have been a lot cleaner and smarter about that. So once I found kind of where that hang up was happening, I wrote my own intersect function, which basically is just the left value of an intersect is basically the maximum of both of their first numbers. So if I have a range of 40 to 60 and a range of 50 to 55, like the first number is 40 and 50, then the max of those two, 50, is where the range has to start. Like anything below either the first values can't possibly be the value. And the same thing in reverse for the max. It has to be the minimum of the two last values. And so if those have anything in between them, so if the high value is actually higher than the low value, then the range exists, or the intersect exists, I should say, and we're going to return that as a new range. And if it doesn't exist, we're going to return that as an empty range. And so that's just basically just doing the math that I would assume that Kotlin would do when you arrange intersects a range. But I assume what's happening again is I think they're just converting that range into a set, converting the second range into a set, removing all elements that are in both sets, which is not going to be the fastest way to do that. Anyway, once I rewrote that, instead of taking a minute per this line over and over and over again, it ran much quicker. So I think that that's kind of the correct solution, although the amount of time it took me to do that was longer than the brute force solution, at least as far as today. So up to you. Anyway, since it's already getting close to the day 6, I will see you in a few hours, I guess. Bye.